Welcome to our discussion on matrices. We're going to look at just some of the basics, how to basically put data into a matrix, how to add and subtract to matrices, find the transpose of a matrix, and multiply a matrix by a scalar, which is just a fancy word for a real number. So first things first, know what everything is so we can talk the same language, right? Our columns are always counted from left to right, and our rows are always counted from top to bottom. So if you wanted to designate where an item was, you give it the row and then the column. So for instance, 40 would be 2, 2 because it's row and column, right? 27, however, would be 2, 1 because it's second row, first column, right? 19, let's do 31 would be 2, 3. 18, right, would be 1, 4, and so on and so forth. So here are the basics of it, right? You can see 1, 1, 1, 2, 1, 3 because it's the first row, first column, second column, third column, all the way down to however many columns you have, and so on and so forth. So that's just so we know what we're talking about when we designate things. Two matrices are said to have the same order, i.e. be the same size, if they have the same number of rows and the same number of columns. So for instance, even though these two matrices both have 6 numbers in them, they do not have the same order. C is a 2 by 3. Again, we do rows first and then columns. 2 rows by 3 columns, 2 by 3. Whereas D is a 3 by 2. 3 rows, 2 columns. The numbers in a matrix are called its entries or its elements. And if you paid attention a couple slides ago, the subscripts, those little numbers that are kind of smaller and below it, correspond to what row they're in and what column they're in. For instance, A23 tells you that that number is in the second row, third column, and so on and so forth. A square matrix is just a special name we give to a matrix that has the same number of rows and columns. Pretty obvious, right? Because then it looks like a square, right? 3 by 3. So it's a square. So obviously anything that is a n by n, right, where they're the same things, 2 by 2, 3 by 3, 4 by 4, those are all going to be square matrix. A matrix that has only one row, such as this or this, is called a row matrix. And if it has one column, it's called a column matrix. So again, kind of obvious naming there. Row and column matrices are also called vectors, right? So that row matrix can be called a vector. That column matrix can also be called a vector. Usually they're called those when we're more in physics. But in economics and business, they're normally just called row and column matrices. Any matrix in which every single entry is 0 is called a zero matrix. So again, we're getting pretty obvious with these names. And we can define two matrices to be equal if they are of the same order and if each entry in each space equals the corresponding matrix. So basically, they have to be identical photocopies of each other, right? They have to be the exact same shape, the same number of rows and columns, and every entry in every space has to be exactly the same in the other matrix. So it kind of becomes silly, to talk about equal matrices because they're just carbon copies of each other. Okay, when the columns and rows of matrix A are interchanged to create a matrix B, or vice versa, we call these transposes of each other and we put a little T above them. Now the best way to see this or best way to understand it is to visualize this. So you can see here's A, here's B, they're exactly the same. So, which element is A32? Well, 1, 2, 3, 3, 2 would be 8, right? Is A a square matrix? Yes. Find the transpose of A. We'll do that in a second. And then does A equal B? Well, oh, nope, look, this 4 is different. So they don't equal each other, right? All right, so here's the solutions, right? We saw that it was 8. Yes, it was a square. They are not equal. And then you're going, okay, how the heck, where does this transpose come from? Well, let's take a look at them side by side. What you can see is the first row becomes the first column. Second row becomes the second column. Third row becomes the third column. And the order maintains itself, right? So Again, if you look at the first column, 103, it becomes the first row, 103. The first row, 137, becomes the first column, 137, right? So everything stays in order. It's kind of as if you would take this corner and spin it. If you could visualize doing that, that's what would happen. Because you'll notice that the diagonal stays the same. Okay, so that's a transpose of a matrix, and we need to use that to do certain types of mathematical operations on matrices. The first ones we'll look at in our addition and subtraction of matrices, and those are really easy. In order to add and subtract a matrix, they have to be the same shape, right? They have to have the same number of rows and columns, because all you're doing is simply adding each entry to the other entry. So if you've got these two matrices that are the same shape, then all you're doing is taking this and this and adding it together, right? See how it's A11 plus B11, and then A12 plus B12, and so on and so forth. You want to note that the sum of A and B is found by adding those two numbers together, right? Each corresponding entry to the other corresponding entry. And we know that, 2 plus 3 is the same thing as 3 plus 2, right? 7 plus 10 is the same thing as 10 plus 7, and so on and so forth. So that tells us that if we add matrix A plus B, it's going to be the exact same thing as adding matrix B plus A, because it's the commutative law of addition. It just means that A and B can commute when you add two things, right? X plus Y is the same thing as Y plus X for anything. Now, if we put a negative in front of the big capital letter that's supposed to represent our matrix, then that just means it's the negative of the matrix, and that just means each element of the matrix is the negative of the corresponding one, right? So whatever the original matrix B was, if you change the sign of every element, so every positive becomes negative and every negative becomes positive, then that resulting matrix is the negative of the matrix. It makes sense. It's, you basically took the original matrix and multiplied it by -1. So for instance, here's our original one. Multiply everything through by -1, we get a +1, a -2, a +3, a +2. 0 doesn't change, right? Because -0 doesn't exist, and -1. And there's our negative matrix. So now, using the negative, we can define the difference A minus B, when A and B have the same order, of course. Remember, same order means same shape. And we can define that as A minus B just equals A plus the negative B matrix. And because we can define it that way, the same rules apply. We just take the first element, we add the second element to it, and so on and so forth. So here's an example talking about the balance of trade. And this table summarizes the actual and projected U.S. dollar value in billions of U.S. exports and imports of pipeline natural gas with Canada and Mexico, and of liquefied natural gas with other countries for selected years. So you can see it's just a bunch of numbers, right? So we could write the matrix that describes the balance of trade in the natural gas. And when we write the matrix, basically all we're doing is just writing down the numbers without labels. Okay, so here's all this junk, right? And you can see that there are 6 columns. So you might be asking, all right, why are there only 3 here and 3 here? Remember, we wanted 1 for exports and 1 for imports. So the first 3 columns were exports, the last 3 were imports. So here are the numbers for exports, here are the numbers for imports. Well, now, the balance of trade we seek is basically the difference of A and B, meaning, how much stuff do we export minus how much stuff do we import, or vice versa, how much stuff do we export minus import, import minus export, just depends on which direction you're wondering. For this, it's how much do we export minus how much do we import. And it makes more sense to do it that way, because then if we get a positive number, it means we're exporting more than we're importing, which means we're most likely making money, right? We have a surplus type of thing. So a positive number is good. So that's what we do. We just 3.15 minus this number, right? 5.76 minus this number, and so on and so forth. And then, as you can see from the resulting matrix, that we didn't do so great. I mean, we've got some positive numbers, but we got a bunch of negatives as well. And then it also tells us where the deficits are, right? Which country are we exporting more to and importing less from? Okay, scalar multiplication. Well, we already saw this because we already saw we could take a matrix and we can multiply it by a -1 and get the negative of the matrix. So if we can multiply it by a -1, why can't we multiply it by a 2 or a 3 or a half or 7, right? We can, and that's just called scalar multiplication. All you do is you just hit every single element, multiply it by that number. Typical example, right? Here's our first matrix. If we do 5a, everything gets multiplied by 5, and there's our result. If we want to do everything by -2, everything hits -2, and there's our result. Okay, so scalar multiplication is pretty simple. And those are the basic operations that we'll be doing with matrices.